All right, so hello everyone. This will be a short little tutorial on how to use LTSpice. If you haven't already looked at lecture 1 for RAP, I suggest you do that first, and that'll give you an introduction on communication systems and amplifiers. So that this will mainly be about how to use LTSpice to simulate simple to complex circuits. So let me close this here. So after you install LTSpice, this will be the screen you see. You have this weird coffee stain looking thing. And to create a new schematic, you either go to File, New Schematic, and press New Schematic, or you can press this little button here, and that'll create a new schematic for you. So in order to start adding components in, you have to go to this top toolbar right here, and there's a few different options. So you have your simple resistor, capacitor, inductor. If you want other components, you can click this button here, and that'll bring up a little menu where you can select from a range of different options. So for this particular example, I'll select a voltage source, which is labeled voltage, and plop it down. And I can press escape to clear that out. And in LTSpice, everything has to be referenced to a ground. And you can create a ground by clicking this button here, or you can just press the G key on your keyboard, and you can connect the negative side of this voltage source to ground. And now I'll add, say, just a simple resistor. And of course, the other side of the resistor has to go to ground. And I'll connect the resistor up to the voltage source. So this is great. We know exactly what this circuit does. We'll know that a current through the resistor of V divided by R will flow. That's just Ohm's law. But you have to set actual values for V and R. So to do that, you just right-click the component you want to set the value for. And here I'll just set a DC voltage of, say, 1 volt. Simple math. And the resistor, I'll just do 1 ohm. So easy enough math. And to actually simulate this, what you do is you go up to the top and press this little running guide, or you can press simulate and run. And if you haven't set up your simulation yet, it'll bring up this window. And so by default, LTSpice will run what's called a transient simulation, which is it'll basically go from t equals 0 to whatever time you specify and simulate everything that happens in between. So in this case, because we only have a DC voltage source and a simple resistor, nothing very interesting is going to happen. So I could just say simulate for 1 second and press OK. And this little black box up here will appear. And what you can do now is press on any node inside the circuit. In this case, there's only one node of interest, which is this guy here. And you see the cursor changes into this little red thingy, which is the symbol for a voltage probe in LTSpice. So I can click that. And you can see a green line has appeared in this black window at the top. And that is the voltage at this node. And sure enough, it says 1 volt from 0 seconds to 1 second, which is exactly what we expect. It shouldn't change. Now we can also measure the current through any component. In this case, we can measure the current through the resistor or the voltage source. And there's a little arrow in the cursor that indicates which direction the current is referenced to. So the resistor, in this case, it's going from top to bottom, so I can click that, and a new line has appeared on top of the green line, so it's kind of overlaying. So you can see at the top we have I of R1, so the current through R1 is this blue, and you can see it's equal to 1 amp on the right there. And that's exactly what it should be, 1 volt divided by 1 ohm. So now let's do something a bit more complicated. Let's create a voltage divider, let's say. So let me delete this line here and add a new resistor. A shortcut to adding a resistor is just to press the R key on your keyboard. And you can move around the schematic by just dragging with your mouse. And let me connect this up here. To connect things, you press the F3 key, and that'll allow you to wire components up. Alternatively, you can press this little button here at the top that says wire. It has like a little pencil and a line, the same thing. So let's make this, say, a 2 ohm resistor. So now we have a voltage divider. We expect the voltage in between the two resistors to be 1 ohm divided by 1 ohm plus 2 ohms, which is 1/3 times 1 volt. So we should expect 1/3 of a volt here. So let's resimulate that. I'll press the running guy. And sure enough, if I double click this, it'll kind of clear the graph up here. So I now see a red curve that says voltage at node 2, which happens to be the name of this node. It's relatively arbitrary. And you can see we're getting basically 1/3 of a volt. And that's again what we expect. And if we were to measure the current, we should expect 1/3 of an amp, because 1 volt divided by 3 ohms gets you 1/3 amps. And I can either measure the current through this resistor or this resistor. I should get the same thing. So let me do that. And sure enough, the green shows me I'm getting 1/3 of an amp. And I can also measure the current through the voltage source, but notice that the arrow is pointing down, which is the opposite current direction of the resistors. So I should get minus 1/3 amps. And sure enough, if I double click that, now that current's in blue, then I'm getting minus 1/3 amps. So that all works out, and that's fine and dandy. Now let's do something a little more complicated. Let's say we had an arbitrary network of resistors, for example, and we wanted to measure what is the input resistance, or like the equivalent resistance of that network. So let's make this thing a little more complicated. Let's say I add resistor here, and another resistor here. And I'll connect these up like so. This is completely random, but I'm just using it to prove a point here. And I'll connect this guy to ground. So I'll say that's 5 volts. I'll say this is 7 ohms, sorry. And this is 3 ohms. So now the question is, if I were at this node here, which is the top of the voltage source, and I were looking into this entire resistor network, what is the effective resistance I'd see? And just by looking at this, I'd say, I don't know, you can do the math, but that's too hard. So what I'll do is something quite nifty. First, let me delete this voltage source and replace it with a current source just to make this process a little easier. And see, now I have a current source, and I can rotate it by pressing Control-R, so I'll make it go this way. And I'll set the current to be 1 amp. The current itself is not too important here. And I'll label the name of this node here, just to make this process easier. So I'll click this tool here up here called Label Net, and that allows me to give a name to a node. So I'll call this one VIN, let's say. Okay, so now let me simulate this. Nothing really appeared because I didn't have any nodes or currents selected. And if I click on this node here, I'll see that the voltage VIN is equal to 2.307 volts or thereabouts. Okay, so let's say I want the impedance looking in. Well, I can straight away say that because I have one amp going into the resistor network, and V over I gets me the resistance, I can say 2.307 volts divided by 1 amp, which is 2.307 ohms, is the resistance. But let's do that in LTSpice. So I can right-click on the name of the thing I'm plotting here. Then I can edit what I'm plotting. So instead of just VN, I'll plot the current that's going through I1, which is the current source, which is 1 amp. And notice how the unit here is changed to ohms. and now it's showing 2.307 ohms. So that is the effective resistance of this network. And if I change this current to be something other than 1 amp, I could say, I don't know, 0.237 amps, completely random. And I rerun the simulation, the resistance should not change because the resistors haven't changed. So that's what we expect. Now, if I change R2 to say, I don't know, 56 ohms, and I rerun this, you see my resistance has changed to something else. Now it's 7.8 or so. So that's how you measure the input resistance of a network in LTSpice. Sorry for the pause there. My bird was attacking me. So anyway, continuing on. So we were able to find the input resistance of an arbitrary network. And that can be very powerful. For example, if we had an amplifier with an unknown input resistance or an unknown output resistance, we could employ this technique to easily find that value. So let's get to a more complicated circuit. For example, one with a transistor. So in order to add a transistor, I go to the component selection window, and I can scroll to the right here and go to NPN. So that stands for NPN transistors. Okay, so I have the NPN transistor, and I'll just plop it down. And so whenever you create or add a transistor to your schematic, you always have to give the transistor some, some model. So, each transistor model that you buy from a vendor has different characteristics. And so you need to tell LTSpice what those characteristics are. And so to do that, you have to right click on the transistor, and you can press pick new transistor. And it'll give you this entire list of built-in transistors. And for this demo, I'll just pick a particular one, which is the 2N4401, which is just a pretty generic transistor. So I'll press OK, and notice how the transistor type is being shown in the schematic. And let's say I want to create a simple switch, electrically controlled switch. So say I want to control the LED, for example. So I can model that LED as a diode, and I can press the diode button up here and select here. And same thing with the transistor, you have to give the diode a model. So I'll right click it and press pick new diode. And I'm not too concerned about what diode I'm choosing here, so I'll just go with the first one. And now I'll connect the bottom of the transistor to ground, and I'll connect this to this, this to this. Okay. So now I want a voltage source to power everything. So let me get one. And let's say I'll put it right here. So I'll have two voltage sources, one to control the power going to the diode, and the other one controlling the base of this transistor. So I'll connect this one up here. Well, first I need a current limiting resistor. So I'll connect that up here. Connect the other side of the voltage source to ground. Let's say I'll give it a 1 kilo ohm resistor. And I'll set the voltage to, let's say 5 volts. So if I were to guess what current's going to flow when the transistor is on in the saturation region, the diode's going to drop roughly 0.6, 0.7 volts. 5 volts minus 0.7 volts is 4.3 volts. So I'll have roughly 4.3 milliamps going through this circuit here. Now on the base, I'll add a current limiting resistor, say, I don't know, 10K. And I'll add another voltage source. So one trick, you can copy a LTSpice component by pressing F6 on your keyboard, and the cursor changes. And then you just click on the component and you can copy it. You can also move components by pressing F7, and that'll change the cursor to this little hand thing, and you can click on a component and move it around. You can also click and drag to move multiple components. And I'll connect those guys up. And we should be good to go. So I'll press the simulate button, the running guide, and I'll make our simulation last for 1 second. And let's see if our predictions worked out. So I can look at the current going through this resistor. And what I guessed 4.3 milliamps, and I was kind of spot on there. I can measure the exact current flowing by right-clicking the name of the current here, and changing attached cursor to first, and that'll give me a little cursor I can drag around. And in this window at the bottom, you can see that the current that's sitting at is 4.279 milliamps, which is pretty close to 4.3 milliamps. So that's good. I can also measure the voltages in this circuit. So I expect the voltage here to be roughly 0.7 volts, and sure enough it is. And the voltage here should be 5 volts. On the base side, I expect the current going through this resistor to be fairly low. It should be 5 volts minus the 0.6 volts from base to emitter of this transistor, which is 4.3 divided by 10 kiloohms, should give me roughly 430 microamps. And I'm getting somewhere around there. So I can get I can get the exact number by putting a cursor on here, and I'm getting roughly 432 microamps. And it's negative because if you notice the current flow through this resistor and the cursor is going from right to left. I can rotate this component by selecting it with F7 and then pressing Control R twice to rotate it around. And now if I resimulate, the arrow is pointing in the right direction, and I'm getting a positive 430 microamps. All right, so that's a basic circuit with the transistor as acting as a switch. Let's try having a transistor acting as a very simple amplifier. So I'll delete all of this, and I press the delete key to do that. And now I'll add back another transistor, the NPN. I'll set it back to the 2N4401. And let me add in a very standard common emitter amplifier. So I'll connect these resistors up there. All right, let me set the values of these resistors. And this will be kind of random. I'm not trying to achieve a particular gain or performance for this. So I'll make the collector resistor, say 500 ohms, the emitter resistor 100 ohms, and I'll set the base to be halfway between VCCs. So these two resistors are equal value. Now let me add a voltage source to create the VCC. And I'll put it right there. Connect the other end to ground. And I'll choose this to be, say, 5 volts. Now I need an input voltage source. So I'll add a new voltage source. And I'll capacitively couple it. And I'll set the capacitance of the coupling capacitor to be, say, 10 microfarads. Okay, and on the output, I'll capacitively couple the output and stick it into a fairly large resistive load, say 100 kiloohms. And I'll also make this capacitor 10 microfarads. Okay. Now, here's where things get a little interesting. I have multiple choices for how I want to simulate this. So let me start with the transient simulation first. I'll set our input to be a sinusoid. Let me show you how I did that. So if I right click on the input voltage source and press advanced, I get a lot more options. So if I go to sine here, that gets me a sine wave. And I'll set the amplitude of the sine wave to be 1 millivolt. I can also write it like this, 1m gets me 1 millivolt. And then the frequency, I'll make it say 100 kilohertz. And I don't have to set any of these other parameters. So I'll press OK. And let me press the running guide to simulate it. And now here's where the stop time becomes kind of important. I have a 100 kilohertz input signal, and a period of 100 kilohertz is, what is that, 10 microseconds? So let's say I want to view 10 periods of that 100 microseconds, of that 100 kilohertz signal. So I'll set the stop time to be 100U for 100 microseconds. And that means the simulation will run from 0 seconds to 100 microseconds. If I set this too high, then basically I'm getting more information than I need, and the simulation will take longer and longer. And at some point, the simulation will take so long, you're just waiting minutes or hours for it to finish. So you do want to keep this as small as possible. For a simple circuit like this, it'll be pretty fast though. So simulation ran, and let me clear this. I can right click and press delete this trace. And let me view the input signal. So we get a normal, nice 100 kilohertz sine wave, as we expect. At the base, if I double click this, you see I also have a sine wave, and you can see it's riding on some DC value. So instead of being centered around 0 volts plus or minus 1 millivolt, now I'm centered at about 1.54 volts plus or minus 1 millivolt. And that's what, sorry, let me, oh, I guess here's a little trap that you might fall into. So remember when I said that the base should be sitting at half of 5 volts because I'm splitting it between 2 equal resistors? And if I double click on this node, you see here that it's not actually 2.5 volts plus or minus 1 millivolt, which should be the sine wave. The reason that is because this transistor is not operating in the forward active region. And I can figure that, I think I can determine that by looking at VCE, the voltage from collector to emitter. And that should be larger than 0.2 volts, or significantly larger at least. So I can do that in 2 ways. One, I can just double click on the collector and I'll get the voltage there. In this case, it's about 940 millivolts. And then I can click on the emitter, which is in green, and that's roughly 850 millivolts. And do one minus the other, and that's clearly less than 0.2 volts. A better way of doing this is, let me delete both of these. I can click on one node and keep holding the mouse and drag to the other node and then release. And it'll give me the difference, the voltage between those 2 nodes. And so here I'm getting the roughly 90 millivolts. So that's less than 0.2 volts, which means our transistor is operating in saturation, not forward active. And that means all of the amplifier assumptions are no longer valid. So let me fix this design to make that design valid. And the problem is that there's too much current flowing from collector to emitter, which causes too much of a voltage drop between these resistors. So let me fix that. Let me reduce the current. Let's say I make this 1 kilo ohm here, and I'll make this resistor, let me make this, let's say 500 ohms. And I'll make this resistor 2 kilo ohms. So now let me rerun the simulation. Oh, 1 kilo ohm. And, oh, I see a problem here. So let me make this 1 kilo ohm, that 1 kilo ohm, and I'll rerun that. And now if I look at this voltage again, you see now that it's now 1.37 volts, which is greater than 0.2 volts. And that means our transistor is now operating in the forward active region. So what I did there is increase this emitter resistor, which effectively decreases the collector current, because remember that the collector current is set effectively by the emitter voltage divided by the emitter resistor. And by increasing the emitter resistor, I've increased or decreased the collector current. Okay, so now let me look at the base again. And you see that it's roughly 2.5 volts, in this case 2.47, close enough, plus or minus this 1 millivolt input signal. Okay, great. So now I can take a look at the output. If I look at the collector, I'm getting a 3.2 volt DC level, which is fine, plus or minus some signal. And if I look at the after the coupling capacitor, which should remove the DC offset, now I get a signal that's centered around 0 volts, plus or minus 1 volt. So let me superimpose the input signal and the output signal. And you can see that they're 180 degrees out of phase. In this case, green is the input signal and blue is the output signal. So they're 180 degrees out of phase, and they're roughly the same amplitude. And that's because this amplifier here has a gain of -1. So we're multiplying that -1 times the input signal. And so this is exactly what we should expect. So let me increase the gain substantially by adding that capacitor here that bypasses the emitter resistor for AC signals. And let me make that also a 10 microfarad capacitor. So let me rerun the simulation. And now take a look at the scale. The scale has changed. We've gone from 1 millivolt amplitude signal, which is the input green signal. And now the output has become roughly 65 millivolt amplitude. So now our gain is -65, which is 65 times greater than what we had before, just by adding this capacitor. So that's the beauty of this design, where we can get a fairly stable collector current DC bias while achieving a high gain. And let's take a look at that collector current. If I click on the current going through the emitter, the collector resistor, we can see that it's roughly 1.8 milliamps. And if you run through the math here, you'll find out that's exactly what it should be. And if I look at the current going through the emitter, it's also 1.8 milliamps. So that kind of verifies that our collector and emitter current are roughly the same. Okay. So now let's take a look at the input resistance of this amplifier. That is, what is the resistance that the input is going to see looking into this node here, into the amplifier? What is the effective resistance? So to do that, let me replace the, actually I can keep it as is. So there's a couple ways to do this. I showed you one way where I replaced the voltage source with a current source of 1 amp and did the voltage across that current source divided by the current to get the input resistance. Let me use a voltage source, so leave this as is, and I'll first flip around this capacitor. You see the current is pointing the wrong direction, so let me flip that around and resimulate. And now I'll delete this trace and add a new one. So I'll add trace. And I'll plot the voltage at V2 divided by the current that's going through C1. Let's see. Oh, sorry, let me first name this voltage here, Vn. So I'll add trace, I'll plot V in divided by the current going through C1. Oh, simulate first. Again, V in divided by the current going through C1. And here we go. So this is the problem with transient simulation. So I have to use a different type of simulation here. You'll notice that the problem here is that I'm taking a sinusoid divided by another sinusoid that are not necessarily in phase, and that could result in dividing by 0 or other mathematical problems. What I really want to do is take the amplitude of one of the sinusoids and divide by the amplitude of the other. So let me fix that. Let me delete these two traces. So what I want to do is use a different type of simulation called an AC analysis. So let me press simulate up here and press edit simulation command and click on AC analysis instead of transient. And so what this will let me do is plot voltages and currents as a function of frequency. So I'll change the sweep type to decade, and that'll allow me to plot frequency in logarithmic scale. And I'll go maybe 100 points per decade. And I'll start at maybe 1 kilohertz and go to 10 megahertz. And I'll put that right here. Now I also have to change the input voltage source. Over here where it says small signal AC analysis, I need to set an AC amplitude. And I'll set that to 1. So the stuff on the left here only applies to transient simulations. The AC analysis only depends on this parameters here. So I'll press OK on that. Now it says AC1, and I'll simulate. So let me try doing this again. I'll press add trace. I'll do V G in divided by I C1. And notice how it says dB here. So in decibels, that's a logarithmic scale. Let me change that to linear. So I'll change that to linear scale. And now we're in ohms. Great. So now we're plotting as a function of frequency, and because we have capacitors here and other circuit components, we expect things to change as a function of frequency. But I really want to know, what is the input resistance roughly around the 1 kilohertz region. So I can create a little cursor here. And that's sitting at 1 kilohertz right there. And I can see that the magnitude right there is about 1 kilo ohm. And the phase is minus 26 degrees. If this was a frequency independent circuit, we'd expect the phase to be 0 across the board. But that's not the case here, because we have the capacitors and there's other non-ideal behaviors of the transistor. There's some reactive components. So anyways, the input looks roughly like a 1 kilo ohm resistor plus some capacitive components. All right, so we found the input resistance. Let's also find the output resistance. So to do that, what I can do is basically take this voltage source from here and move it to the output. So let me delete this resistor, then I'll delete the input here. And I'll connect up the voltage source to the output. And I'll label this as the out. And rotate this capacitor around just so it's pointing in the right direction. And I'll rerun the simulation. So let me add a new trace. Then I'll do V out, V out divided by the current going through C2. And this will give me the output resistance of this amplifier. And the output resistance should be fairly close to the collector resistor. And if I look at this plot, you see as I go to lower frequencies, sure enough, the output resistance is roughly 1 kilo ohm. And if I put a little cursor there, at 1 kilohertz, the output resistance is roughly 880 ohms, which is pretty close to 1 kilo ohm. And the phase is 156 degrees, which means that we're getting more it looks inductive, which is just a property of this circuit. So what we did here is that we took away the input because the output resistance doesn't depend on the input. And we feed in a signal into the output and measure what current flows. Sorry, this capacitor is facing the wrong way. Let me redo that. And now the phase should make more sense. So now the phase is minus 23 degrees. So we should expect the output capacitance to be capacitive, not inductive here. But the magnitude is the same, it's 880 ohms. So anyway, what we did is we took away the input, we fed in a signal into the output and measured the voltage divided by the current, which should get us the resistance. So this is about 880 ohms, right? So let me put this back on the input. Connect it back up. And put the resistor back in. And let me disable the AC analysis. So to do that, I just right-click on the AC analysis. It'll bring up this window, and I'll put a semicolon instead of the period here. That basically comments out that line. And under the transient part, I'll replace the semicolon with a period. And that'll re-enable the transient simulation. So I'll run this. Then I'll click on the output. Oh, I forgot a coupling capacitor here. Let me add that back. And I'm getting back my 65 millivolt amplitude signal. Now remember that the output resistance here at 1 kilohertz was roughly 880 ohms, which means if I put another 880 ohms as the load, we should expect that the output voltage should drop by a factor of 2, because now the output voltage is being split between the output resistance and the load resistance in a voltage divider sense. So let me re-simulate that. Remember, we had a 65 millivolt amplitude before. Now it's roughly 32 millivolts, which is about half of 65. So that's exactly what we expect. So I hope that gives you some idea of how to use LTSpice and how to build amplifiers and simulate them in LTSpice, as well as measure their input resistance, output resistance, and gain. Hope that helps.